Unit 1 Climate Science. In this unit, I will cover climate system, cycles and processes, positive and negative feedbacks, natural and human causes of climate change. Climate system is extremely complex. It's much more than just the atmosphere. In fact, climate system includes it all: the atmosphere, the sphere of air, the hydrosphere, the sphere of water, the biosphere, that includes plants and animals, the cryosphere, the sphere of ice and snow, the lithosphere, the sphere of rocks and animals, and finally today it's also the anthroposphere, the sphere of humans, us. This diagram shows various connections in the complex climate system. In fact, we would come back to this diagram many times in the next unit on climate modeling. Everything in climate system is driven by forces that can be internal or external. The best example of the natural forces is the energy of the sun. Everything in this climate system is interconnected through many different processes. For example, the ocean is connected to the atmosphere. The atmosphere is connected to the biosphere. The biosphere is connected to the lithosphere, and so on and so forth. In climate modeling, we will use the term coupling. The climate system is a coupled system. It includes many coupled tight connections between all these different spheres. They're interconnected through a variety of different processes and cycles. Some of these processes include energy flows that connect different spheres, the water cycle, and the biogeochemical cycles. In this class, we would need to pay attention to the nitrogen cycle, oxygen cycle, carbon cycle, phosphorus cycle, and the cycle of sulfurous. This diagram illustrates the interconnectedness of the system through the energy transfer. The solar energy is coming into the atmosphere, and it's partially reflected, partially absorbed. It can be reflected by clouds, it can be reflected by small particles that are called aerosols. Part of it then is going to be absorbed by the surface of the Earth, by the biosphere, the lithosphere, and the surface of the ocean. Some of this energy is going to be transformed into other forms of energy. Part of it is going to be irradiated. Part of it is going to change its form. In fact, it's coming into the atmosphere as a shortwave radiation from the sun, and then as it is re-radiated and transformed, it's reflected back as a long wave radiation that is partially trapped by clouds and greenhouse gases and partially going back into the outer space. Another example of tight coupled connections between different parts of climate system is of course the hydrological cycle, the cycle of water. The hydrological cycle involves 5 major processes such as condensation, precipitation, infiltration, runoff, and evapotranspiration and evaporation. Carbon cycle is an extremely important cycle in our climate system. In fact, each of these spheres, the ocean and the hydrosphere, the atmosphere, the lithosphere, the biosphere, they all contain carbon sinks and carbon sources. And the largest carbon sink by far is the deep ocean. Other important carbon sinks include vegetation and soils and the atmosphere and also the surface ocean. Carbon is moving through many natural processes, including photosynthesis and respiration and decomposition, from one sink to another. Some of these movements are very fast. Some of them are much slower. Carbon might be staying in some sinks for several hundred years, for thousands years in others, and for millions years in some others. As we are burning fossil fuels such as oil and gas and coal, we are releasing carbon that was stored in the vegetation many, 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 many million years ago. Think of this as using your bank account that was built by many, many generations of your ancestors and spending it just perhaps in 1 minute or 30 seconds. This would be identical to what we are doing now with carbon that have been accumulated for many, many million years since the time when dinosaurs were roaming our planet. And we're using this extremely concentrated carbon-rich resources during a very short period of time or since the beginning of the industrial times. Although most of our attention would be paid to carbon cycle for its obvious, very important role in the climate system, it's important to understand that all major chemicals in the atmosphere and in the climate system are connected. And nitrogen cycle is one of the prime examples of another biogeochemical cycle, which is very much linked to climate change and carbon cycle. Nitrogen is present in the atmosphere. In fact, it's the most abundant gas. It's also present in soils, in biological life, in animal proteins, and in our soils. And it's extremely important for the health of our vegetation and production of our food. Another noteworthy biogeochemical cycle, which will be important for our understanding of climate system, is the cycle of sulfur. Again, sulfur is an important part of biomass. It is present in soils, it is present in vegetation, and it's extremely important for its health. It is also a part of the atmosphere in the form of various emissions. We will talk about these emissions later because some of them might have warming impact on the atmosphere, and some of them, in the form of aerosols, might actually have cooling impact. And finally, the cycle of phosphorus. Differently from nitrogen, carbon, or sulfur, phosphorus is actually not present in the atmosphere. It can be found in the atmosphere only in the form of suspended particles, the aerosols. But it's another component which is very important for our soils and our vegetation, and it can also have adverse effect on our water resources as it's leaching from soils when they're over-fertilized. It has also very important impact on the health of our agriculture and our natural ecosystems. Everything in climate system is connected through the series of biophysical feedbacks. Some of these feedbacks are negative, others are positive. Negative and positive feedback mechanisms can be found in any complex system, in a human body, in a biological system, in an economic system. Negative feedback is a feedback that is bringing the system back to its homeostasis. The homeostasis is the state of stability. So a good example of this could be a thermostat in your house, because it always brings the temperature to where you want it to be. A positive feedback, on the other hand, is throwing away the system more and more away from stability. It is happening when one process that starts the change in the system causes the other process, and the outcome of the second resultant process is in turn creating a loop, and it amplifies this original process that causes the second process. And so the process is going on and on and on and on, and each time the amplification is leading to enforcement of both the first and the second process. So what is the role of these positive and negative feedbacks? They are a part of both natural and human causes of climate change. Climate has been changing for the past 4.6 billion years, as long as our planet exists. We are going to start by exploring some natural causes of climate change that will help us later to understand how human impact is shaping our climate today. So some of the natural causes of climate change include Milankovitch variations, solar activity cycles, changes in the atmospheric transparency, changes in the ocean circulation, and volcanic activity. The Milankovitch cycles are the three astronomical cycles that describe the relationship between the Earth and the Sun and the amount of solar radiation that is reaching the surface of our planet. They're called the Milankovitch cycle by the name of the Yugoslavian scientist who described them for the first time. Those are three overlapping cycles: the 96 or 100,000 year cycle, which is the cycle of eccentricity or the shape of the orbit of the Earth, the 40,000 year cycle, or the 42,000 year cycle, as you will see it sometimes. It's the cycle of the tilt of the Earth. In fact, the tilt of the axis of the Earth is changing from 25 degrees to 20 degrees, and it determines the position of the Tropic of Cancer and the Tropic of Capricorn. And finally, the 20 or 21,000 year cycle, which is the cycle of precession that describes how the Earth is moving on its orbit, which is responsible for the angle of the Sun over different parts of the Earth and the run of the seasons. The Milankovitch cycles overlap, and they fit perfectly well with what we know from the isotope records about the temperature of the Earth over many thousands and even millions of years. In these records of standardized isotope oxygen-18, you can see the pattern of all these three cycles happening at the same time. The changes in the solar radiation caused by Milankovitch cycles might be quite small, but they're sufficient to trigger the initial change. The rest is happening because of the positive feedbacks that are the integral part of the climate system. So let's imagine the situation when, as a result of the Milankovitch cycle, our planet starts receiving slightly less solar radiation. This in turn is leading to the slight decrease of the temperature. As the temperature is declining, we see more and more the buildup of the snow, buildup of the glaciers, buildup of the sea ice, and all this is leading to the increase of the albedo. As we see more and more ice and snow building up, more and more energy is irradiated back into the atmosphere, and less energy is absorbed. So the planet is becoming slightly colder, and again slightly colder and slightly colder every single year. And each year it's receiving more and more ice, and the process is continuing through the positive feedback until it reaches a certain tipping point. The glacials are building, and we are moving into the glacial period. Let's imagine the opposite situation. Something triggers, in this case, Milankovitch cycles. Maybe the cycle of eccentricity brings slightly more solar radiation. This in turn is leading to slightly higher temperature. And then the albedo starts declining, the amount of sea ice is declining, the sea level rise start increasing. We see the changes in the sea surface temperature, we see changes in the thermohaline circulation, and overall our planet starts moving again into the interglacial. So there is a number of positive feedbacks. One of them is through the albedo, the amount of energy that can be reflected or absorbed by different areas. The other mechanism is the thermohaline circulation. Some other mechanism includes positive feedbacks that are involving the amount of methane that is thawing from the permafrost and going into the atmosphere. So all these positive feedbacks are then amplifying the initial cause of the temperature increase due to the Milankovitch cycle. Later, we are going to apply the same mechanism in order to understand how exactly the same positive feedbacks are now amplifying the human impact on the environment, which is happening way much faster than this 96,000 or 40,000 or 21,000 year cycles are caused by the Earth-Sun geometry. So one of these amplifications or positive feedbacks is happening as a result of thermohaline circulation. A thermohaline circulation is the circulation of temperature and salinity. In fact, this is the ocean conveyor belt. It's a system of all ocean currents that is caused by two major gradients, the gradient of salt and the gradient of salinity. In the normal circumstances, when the system is in balance, we see really two major processes that are happening all over the world. Warmer water is moving up, colder water is moving down. The saltier, heavier water is sinking, the lighter, fresher water is moving up. At the same time, the colder water is moving away from the polar regions towards the equator, and the warmer water is moving away from the tropical areas, from the equator, towards the polar region. And we have the Coriolis effect that is moving everything to the right in the clockwise fashion in the northern hemisphere, and to the left in the counterclockwise fashion in the southern hemisphere. So we see this system of deep and surface currents that is constantly moving water from between the equator, through the surface of the ocean, to the polar areas, such as the Gulf Stream, for example, the North Atlantic Current. Then the colder water is sinking, it's moving back along the bottom of the ocean from the colder areas back to the equator, and then the process essentially is looping and continuing. The thermohaline circulation can be disrupted by two things: when we have the major change in the temperature of the water, or when we have the major change in the salinity of the water. This can happen again either as the result of amplifications initially caused by the Milankovitch cycle, or as it's happening now as a result of human activity, when the weather is getting warmer and warmer and warmer, when our climate system is warming up over many years. Eventually the glaciers are melting, and this is in turn is adding more fresh water into the ocean. The initial salinity band is upset, and more fresh water is moving into the ocean. At the same time, the temperature of the ocean is also changing. The ocean itself is warming up. It's also thermally expanding, and this is changing the gradients of temperature as well. So think of these two important gradients, the gradients of the temperature and the gradients of salinity. If these gradients are changing, if the gradients are reduced, and this is exactly what is happening right now with the gradient of salinity especially, the ocean currents are slowing down, and we see already some evidence that the Gulf Stream, the North Atlantic Current in the Atlantic Ocean, is already slowing down. So the Milankovitch cycles are operating at the scale of many thousands of years. They are very long-term, and they are explaining the pattern of our glaciations and interglacials. These cycles are further amplified by various positive feedbacks. The Milankovitch cycles should not be confused with the cycle of solar activity. The sunspot cycles are very short-term and they have very minimal impact on the changes in our climate system. Volcanism is another phenomenon that has a significant impact on the global climate. In fact, volcanoes can be both sources of aerosols that are contributing to global cooling, or when volcano is not erupting but is active, they can be also sources of greenhouse gas emissions. Now, it is important to realize that all the greenhouse gas emissions coming from volcanoes today are much, much smaller than the anthropogenic greenhouse gas emissions. Volcanoes had been playing important role as coolers of the present atmosphere. For example, we know that after the eruption of Mountain Helen and Mountain Pinatubo, there were a couple of years that when the temperatures were significantly lower than the average. Usually these aerosols are hanging in the atmosphere just for a few years, typically 2-3 years maximum, and then the cooling effect is going away as the aerosols are dissipating in the atmosphere. However, if the volcanic eruption is very significant, this effect can continue longer. For example, when the mountain Krakatau in Indonesia erupted in the 19th century, there was a year without summer all over the world when the snow was falling in the areas close to the equator, in Africa, in India, in the areas where people have never experienced snow before. What was more frightening, that the snow sometimes was red or it had other colors because of the chemicals that were present in the atmosphere from those aerosols. And people was, of course, were thinking that this is the end of the world because they have not only they have never seen snow in their areas, but also the snow could be the color of the blood. So today we know that, of course, this is not the end of the world. It's just the impact of the aerosols that might be actually contributing to slight cooling of our planet, typically for a couple of years after volcanic eruption. An exception would be a supervolcano, something like Yellowstone. Computer models suggest, and also the geological data from the past suggest that if a supervolcano such as Yellowstone erupted, we would be propelled into many, many years without sunshine. And that would clearly trigger some positive feedbacks that would propel our planet into another glaciation. So scientists know that climate has been changing for thousands of years as the result of these various natural causes. The CO2 concentrations in the atmosphere that have been revealed in the ice cores drilled in the Arctic and in Greenland tell us the history of the CO2 concentrations in the atmosphere and of its connection with the temperature of the Earth. Here is the history of our glaciations and interglacials, and we know that for many thousands of years, CO2 concentrations have been changing, following roughly the pattern of Milankovitch cycles. They have been following the pattern of the temperature of our planet. And we have experienced many ups and downs, and now here we are. So there is also something else going on with our planet, in addition to the changes that have been caused by the natural phenomena. So how can we separate the human and natural influences on climate? How do we know what are the effects of natural causes and what are the effects of human causes? How we can explain climate change that is happening today and is affecting us all? This graph shows you the changes in the global temperature And their explanation from what we see today from the observation and what fits with both natural and human factors and natural factors only. So if we could subtract the human impact on climate and think only about climate changes that can be explained by Milankovitch cycles, by volcanic eruptions, by changes in the solar activity, this is what we would see in the 20th century and the 21st century, right? We would see roughly the same variability that has been going on in the past, but we are not in this pattern anymore. Something else is going on, and something else is probably much stronger than all these natural causes together. Today, there is a very strong scientific consensus that along with all these natural causes of climate change, it's the anthropogenic climate change or man-made climate change that is affecting our planet in a much more profound and much faster and the most dramatic ways. And it's about human impact on climate change that we need to worry today, not about very slow and insignificant natural changes. There are four major ways how humans are impacting climate. Through the greenhouse gas emissions, the so-called global warming is by far the most prominent part of anthropogenic climate change. But we are also contributing into very slight cooling. So the global cooling is significantly lower than global warming. Just as volcanic eruptions, our industrial processes are also emitting aerosols that have opposite effect on climate compared to greenhouse gases. We are also contributing to climate change through the destruction of the ozone layer in the stratosphere. Unfortunately, this process has slowed down quite significantly due to the reduction of the CFC emissions. So even though the stratospheric ozone holes are still the reality, they are not as prominent, not as dangerous today as what it used to be in the 1970s or 1980s. And the last but not the least is the changes in land use and land cover. That is another very significant contribution into global change, perhaps the second major contribution after the global warming caused by the greenhouse gases. So all the meteorological data from various centers, from various countries tell us exactly the same story. The temperature of the Earth has been increasing very significantly, and this increase has been even more prominent since the 1960s. The greenhouse effect is extremely well understood, and in fact, the greenhouse gas effect itself is a natural phenomenon, and it's an important part of our climate system, which is responsible to that Goldilocks effect of our planet, where the conditions are really just right for the biosphere. They're just right for the life on our planet. If the greenhouse effect was more significant, our planet could be too hot, just like Venus. If the greenhouse effect was less significant and our atmosphere was less dense, like in Mars, our planet would be just too cold for the biological life. But the natural greenhouse effect is maintaining perfect conditions for life on our planet. What is happening is that the shortwave solar radiation is coming from the sun, it's going through the atmosphere, it's then re-radiated in the form of the long wave radiation or thermal infrared from the surface of our planet. And most of this heat is escaping back into the space, but part of it is then re-radiated by the greenhouse gases, by the CO2, and then other greenhouse gases in the atmosphere. And this is what creates this warm blanket around our planet, making life possible. However, when we have too much of this protective effect, that creates problem. So as the same shortwave radiation is coming from the sun, more and more energy is trapped inside of the atmosphere as we see more CO2, more methane, more nitrous oxide, more CFCs building up in the atmosphere. It makes more and more difficult for this long wave thermal infrared to escape the atmosphere, and essentially this heat is becoming more and more trapped. So today there is really no controversy that the current climate change that we are experiencing in the 19th, 20th, and the 21st century is primarily caused by human activity. There is a very strong correlation between the buildup of the CO2 and other greenhouse gases caused by our industrial activity and the increase of the temperature. If you look at the temperature history from the paleoclimate data and compare them to the modern temperature increase reconstructed from the meteorological data, you can clearly see that the present warming is unprecedented, and it's shows us the story that we have never experienced before. In fact, our planet today is warmer than it has ever been in the past 1,000 years, and possibly much longer. We are also having much higher concentrations of CO2 that we have ever experienced in many thousands or even millions of years. So I want to come back to the slide that we saw before, just for a moment, to show this remarkable correlation between the meteorological data and the model data from various data sets and climate models that are telling us the story of global warming since the beginning of the industrial period till now. And we can use climate models, the mathematical models that help us to see the difference between the natural forcings and the human forces and their role in the climate system. And so what we see here of what would be our temperature today if only natural forces were shaping our climate. So our temperatures would be significantly lower. This is what we would experience right now. We would be going through slight coolings caused by several volcanic eruptions, including El Chichon, including Pinatubo. But instead of being somewhere here, we are actually here. So this temperature increase cannot be explained by the natural causes of climate change. In fact, the present pattern of the temperature can only be explained by the anthropogenic forces. So this is where we are right now. And this is what the models predict for us right now if we combine both natural and anthropogenic causes of climate change. So this is what is modeled and this is what is real, and you can see very significant correlations between what the mathematical models predict. And we can run these models against the past and see that they're pretty accurate, fitting with the real meteorological observations. And this is what they tell us about climate right now and the role of anthropogenic and natural causes of climate change. So these measurements from the Mauna Loa Observatory in Hawaii tell us a story of changes of the CO2 concentrations since the 1960s till today. In fact, you can go to this website yourself and check the full record from the observatory till the present day. Here you see my slide that I downloaded August 9th, but these data are available daily, And you can see how quickly the CO2 concentrations have changed, going from 310 to all the way to 410 particles per million. It is also interesting to see this breathing variability. Every year, the CO2 concentrations in the atmosphere are changing, of course, due to the changes of the biomass. But overall, we see this progression due to the growth of anthropogenic emissions. So many million years ago, when the dinosaurs were roaming our planet and humans didn't exist, and huge ferns were dominating our biosphere, there was a very different climate and it was a very different world. And eventually all these dinosaurs and all this vegetation became coal and oil and natural gas, and it took many million years to build those fossil fuels. Today, we're extracting them and we're releasing them at the unprecedented scale, and we're essentially burning this ancient sunshine that our planet accumulated over millions of years, and now we are releasing it at the rate of days or years. It's really like burning your bank account that you have built for many, many generations and then spending it just in one day. So we're dumping about 110 million tons of man-made global warming pollution into the atmosphere every 24 hours. And we are not really fully grasping yet with the full scale of the amount of heat which is released as a result of burning of fossil fuels, because most of this heat is actually ending in the ocean. Our warming would be much, much faster if our planet was not primarily covered by the ocean. So the majority of this energy, the majority of this heat is ending in as ocean heating, and then only a very small part of it is going to the land, the atmosphere, and the ice heating. But it is leading to the drastic changes in the ocean that are still contributing at a much slower rate to the changes in the climate system. So you can think of this as exploding 4 Hiroshima bombs per second. If you think about the amount of heat, the amount of energy which is going into our ocean as a result of all these fossil fuels that are burned, it's unprecedented, right? We have burned essentially 2 billion atomic bombs, or the equivalent, since just 1998. So here is the breakdown of CO2 emissions per region or per country. We can see that about 28% of global emissions are coming from China, which is of course a huge country with a huge population. The United States is responsible for 14% of global emissions, even though our population is significantly lower. India about 7%, another major country in terms of its population. And then this is where the rest of the world, right? So this is where we see Russia with its 5%, Japan 3%, Germany 2%, and so on. This is the breakdown of carbon emissions by economic sector for the world. This breakdown will be different for the United States, and we're going to explore this a little bit later. For the world, however, the majority of the emissions is coming from the electricity and heat production, and this is 25%, followed by 24% coming from agriculture, forestry, and other land use changes, followed by 14%, followed by 21% from industry, and then 14% from transportation, and then also some other energy production and the buildings. For the US, this breakdown will be different with much more coming from transportation and industry. So that will be kind of counterbalancing agriculture. Our emissions from agriculture are a little bit less than 10%, but it just gives you a general picture of where these emissions are coming from. So global warming caused by the enhanced greenhouse effect caused by anthropogenic carbon emissions is by far the major impact on climate change. However, there are some other ways how we're impacting climate. One of them, paradoxically, is contributing to cooling caused by the aerosols. So the aerosols are small particles in the atmosphere that could be ash, soot, dust. Those are usually either solid particles or droplets of liquid. This can be droplets of liquid changed with chemicals, producing various anthropogenic acids that can be contributing to relatively short-term cooling of the atmosphere. The same effect can be observed as a result of the pollution of clouds. So if we compare the polluted cloud and normal cloud, the polluted cloud can actually screen some of the incoming solar radiation and slightly offset the global warming. The same is happening when we have lots of aerosols. Essentially, the atmosphere is becoming so polluted that some of the incoming solar radiation is just screened away and it cannot reach the surface of the planet. Should we use the aerosols to offset global warming? Certainly no. Aerosols have many other dangers. They contribute to asthma and other respiratory diseases. They're just harmful for our environment. They're destroying vegetation. So injecting aerosols in the atmosphere is definitely not a good way to regulate global warming. So the third group of processes that is associated with human impact on climate system is the depletion of the ozone layer in the stratosphere. Now, it's important to understand that the ozone can be found in the troposphere and in the stratosphere. When we find the ozone in the lower level of the troposphere where we live, this ozone is entirely caused by man-made pollution. So you have probably heard before about the days when the ozone levels are too high. This is the anthropogenic ozone. This is a pollutant, and it has very negative impact on our lungs, on our eyes. It can be dangerous for animals, for humans, for plants, and it's entirely man-made. So we're not talking about that ozone that we really need to keep at the minimum. The ozone, the O3, is also can be found in the lower layer of the stratosphere where it occurs naturally. So we need to, here we are talking about the depletion of the ozone in the stratosphere, not in the troposphere where it is man-made. We worry about the destruction of the natural ozone in the stratosphere. It's important because it absorbs ultraviolet radiation and it protects us, it protects the biosphere, it protects life on our planet from the harmful impacts of ultraviolet radiation. There is somewhat confusion between global warming and the depletion of the O3 in the stratosphere, although those are two completely unrelated and completely different processes. They're probably often confused because they have the same cause. They're caused by human activity. They are both caused by the release of pollutants. And it can be also caused by the same pollutant, which is CFCs. So the CFCs and halogens, they are both very potent greenhouse gases. They're synthetic, they're entirely artificial gases They don't exist in the natural world. And those are the same substances that are also contributing into the destruction of the ozone in the stratosphere. Where they're coming from, the CFCs, they used to be found in the aerosol sprays, in deodorants and hairsprays, in the refrigerants. And when they are released in the atmosphere, they can be extremely dangerous because they are binding the third atom in the O3. Today, this is much less of an issue because it's a result of successful implementation of the Montreal Protocol. There have been very strong international agreements banning the production of CFCs, so the CFC emissions have decreased since that time significantly, and we can only hope that eventually Paris Agreement would have the same success as the Montreal Protocol as we start being more and more serious in addressing the greenhouse gas emissions. And finally, the fourth group of factors associated with human impact on climate change is associated with land use and land cover changes, the so-called LULCC, land use, land cover change. So there's a very strong connection and kind of mutual amplification of climate change and land use, land cover change, because the current land use practices make climate change even worse. On the other hand, the land is increasingly damaged by climate change, and the climate change is changing our agricultural practices. So you know that land is a net carbon sink. Vegetation and soils are both carbon sinks, but as we are destroying them through land use and land cover change, it also is leading to the increase of carbon dioxide emissions. And the land-based climate solutions can also at the same time reduce carbon emissions and remove some of this carbon from the atmosphere into the atmosphere. So we really need to look more into those practices and promote agricultural practices that create incentives for creating more carbon sinks. Land-based climate solutions, of course, have many benefits beyond just curbing climate change. There are many ways how we can use the land at the same time for healthier production of food and at the same time production of energy and at the same time as a carbon sink, and there are so many benefits for doing this. Some land-based climate solutions can be also somewhat controversial, and they can carry risks and trade-offs of their own. If we think about production of the biofuels, you need to think if it's really worth it, because sure, it can be reducing our dependency on fossil fuels such as oil and gas, but on the other hand, biofuels are also sources of carbon emissions, and they can also be sometimes a threat of food security if we reallocate the land that is used for the production of food to the production of fossil fuels. It can also cause many other environmental problems. So those are issues that we definitely need to be very attuned to and look into how land use and land cover are related to climate change. So land is both a powerful sink and also a source of carbon dioxide emissions. If you think about the balance between respiration and photosynthesis, as a net effect, land is a carbon sink. It sequesters about 6 gigatons of CO2, which is an equivalent of total annual greenhouse gas emissions from the United States. By land, I mean vegetation and soils. And so this is definitely food for thought of how better land use practices can play a very powerful role in helping us to reduce emissions and sequester part of this carbon which is already emitted into the atmosphere, and how it can help to regulate our climate. So land cover and climate are related in many ways, not only through carbon emissions, but also through hydrological cycle, through heat exchange that we discussed in this lecture earlier. So if we look at the local scale, what we see here is actually the impact of the regional climate changes caused by land use and land cover changes, such as, for example, deforestation or urbanization or overgrazing. In this case, what we see here is the simulation of overgrazing on the prairie landscape as the vegetation is changing, have shorter. If we move from the tall native prairie to the short prairie that we see at the bottom of the slide, as we see less vegetation, less moisture is available for the production of the clouds. When we see more clouds, we see as a result the decline of the rainfall, and then this decline of the rainfall is leading to further degradation of vegetation. And so here you see a classical example of positive feedback. Remember that positive feedback is that loop when one initial process is causing the second process, which is in turn amplifying the first process. So when we see the destruction of vegetation, it leads to reduction of precipitation. The reduction of precipitation is leading to further degradation of vegetation, and so on and so forth until we see, total degradation of the system to desert-like conditions. And this is exactly what is happening in the areas that are affected by desertification. So the desertification is this one of the land use, land cover processes leading to this extreme anthropogenic kind of fully degraded desert-like conditions where vegetation basically cannot grow anymore, and you have complete change in the ecosystem. So I just want to very quickly summarize. In this unit, we have covered the climate system, the major connections between different components of climate system, the role of the biogeochemical cycles, and the causes of climate change, the natural causes and human causes of climate change, and the way how they're all interconnected through and amplified by positive feedbacks. The readings for Unit 1 include the National Climate Assessment Volume 1, Chapter 1, where you would find lots of information about climate change. The NCA Chapter 2, the Climate Modeling Primer, Chapter 1. You can access the Climate Modeling Primer through the library access. And the Blackboard online resources for the climate system, where you would find visualization tools for each of these processes and causes of climate change that we have discussed in this lecture. I also recommend that you watch the NASA videos that are posted on the Blackboard, including the NASA video about the temperature changes, and then the National Geographic video about the causes of climate change.